I'm going to talk about some of the challenges and opportunities for offshore wind energy. And so let me start with describing advantages. And the advantages are sort of important to bear in mind because there are challenges, which I guess we can also consider opportunities. But the advantages are so significant that it's, I think, very much worth our effort to try and see how we address some of these challenges. So one of the important ones that we recognize is long design life. As has been experienced in the North Sea and in other locations, the very large oil and gas structures have performed extremely well for those who have been out there for decades in the field. Steel has not generally performed quite as well. We recently finished a project for the US regulator for offshore wind on corrosion fatigue of offshore wind support structures. And there are challenges on the outside, as well as even in some ways more challenges on the inside of these large monopile structures. In design, the general approach is that you try and have corrosion protection via coatings and cathodic protection cover you for 10 to 15 years, and then you try and get another 10 to 15 years out of the structure with free corrosion. For the oil and gas industry, which of course have used a lot of steel structures in the marine environment, the situation is quite a bit different because those structures are manned. There are fewer of them for the amount of energy being generated. And so they have, and also you do not have high stress fatigue loadings in the same way that you see in offshore wind structures. So some of our strategies for corrosion repair in the offshore oil and gas for steel structures do not make practical economic sense for offshore wind energy. One of the other advantages that we're all very familiar with concrete is through the use of precast or post-tensioning. We can reduce or eliminate cracking during operation. We can also use non-ferrous reinforcements if we want to guard against corrosion. But even as I say that, we also know that for offshore concrete oil and gas structures that have had heavy reinforcement, that's 3 inches or so away from the outside surface, even after being there for decades, they exhibit very good performance. Of course, concrete, we can use other types of reinforcement materials such as textiles and fibers, non-ferrous fibers, which can yield even greater improved performance. And of course, Jason already mentioned some things on the horizon. And obviously, we have a lot to understand, particularly in the areas of durability, as to other types of concretes would be suitable for the different environments. One of the great advantages of concrete, of course, is you can cast it in virtually any shape. So if you feel you have an area of a stress concentration, it's a little bit easier to change the geometry to address it. One of the other nice aspects of concrete in terms of its stress strain response and time-dependent behavior, if you do have a hot spot that has high stresses, often that will relieve and those loads be spread. But Sihan spoke about concrete support structures for onshore. There has been concrete spars that have been used in the north off the shores in Scotland that were developed by Equinor in a number of partners. And I know that Olav Olsen was involved in some of the recent project for Tampen as well. We have a number of different concrete gravity base solutions that have been used with different types of methods of ballasting. We have floating structures. This is one out of Maine that is being developed with support from the Department of Energy. This is the structure from Olav Olsen that Troy spoke about. This is an interesting concept from Mistako, and what they do is they actually have a telescoping tower. And what this enables is to put the nacelle in the rotoron in a low position so that you're stable during tow out, and then it gets teleported, then it gets telescoped up after you're in the field and anchored down. And then in the top right, what you see is suction buckets, which Jason also spoke about. Float and sink solutions offer some great advantages. As is shown here, these are ones from the Bly demonstration project. They were cast at Newcastle, and these are being towed out before they're dropped down on the seabed. One of the things that makes float and sink advantageous is, of course, it reduces the need for heavy tow-out vessel or heavy vessel to lift out the foundation. But perhaps even considerably more important is you can not have to use pile driving. One of the challenges with pile driving is you can produce noise of about 160 decibels. What is presently done in practice is people put on these bubble curtains, which are quite expensive. Perhaps $500,000 is the number I typically hear for what this costs. And so as you drive the pile, that helps break up the noise so that the sensitive marine habitat are not impacted. And in the US, North Atlantic, it's the North Atlantic right whale that people are very concerned about, who do calls over hundreds of kilometers to their fellow whales. So you can reduce the noise substantially with bubble curtains, but still you get an awful lot of transmission. Another advantage of concrete structures is, and this was mentioned before, when you go up to something slightly larger, concrete becomes more and more competitive. As it was also mentioned, we are getting larger and larger turbines. I thought it would be helpful to show one where you actually see the size of the turbines relative to people. So this is General Electric's 12 megawatt turbine. This is it going into the dyno tester in Bly in the UK. This is where a blade would connect onto this turbine. This is one of those blades being transported to, this is actually after it was transported to the Wind Technology Testing Center, which is a few miles from where I'm located. The blade is 107 meters long. One of my colleagues at Tufts designed the Wind Technology Testing Center, and they did it for 3 90-meter long blades. Everybody thinking, well, of course, we're never going to need to test anything that is longer. And so now this is 107 meters. So challenges to do the certification are out there. This shows, and others have showed as well, some of the evolution in the size of turbines getting increasingly larger. And this was the 12 megawatt, but it doesn't stop there. So this was a very recent announcement. So Equinor said that for their Empire Wind project, they're going to use the Vestas 15 megawatt turbine, which has a rotor diameter of 236 meters. And it is 100, and they're ordering 138 of them. So there's quite, so the sizes continue to increase as people were indicating, and there are many benefits for that for cost. One of the other benefits is that it means you space the turbines a lot further from each other. And that is a very important thing for the fisheries community because their buy-in is very important. Local manufacturing jobs. One of the things that concrete does lend itself to is lots of good employment opportunities. It is not impossible, but it is more difficult to ship the concrete support structures longer distances than the steel monopiles, which means there's more of an incentive to do the construction locally. We've not been necessarily very good at calculating the economic benefits of that when we make selections for different proposals for what should be done. Another, and this was also mentioned already by Marcus, about fatigue. Steel, concrete, generally speaking, is much less susceptible to fatigue concerns. So this is the small, now almost 8 meter diameter can for a monopile. The thickness of these walls can easily be 6 inches. And so this is a view of the welding, the heat affected zone, and the cracks that often appear at the toe of these structures. And you can get concerns with pitting corrosion that develops on the surface that then leads to this type of a cracking. And it's a difficult situation that the industry has to deal with, but it is a major factor on operational lives that can be achieved. Concrete, and we are doing a project right now for the Department of Energy on concrete fatigue. And we are generally finding that concrete does extremely well, even at various stress levels that you would expect to see for different designs for supporting offshore wind turbines. So this is sort of a number of the very important advantages, and there are challenges, and I'm going to talk about two types of challenges, ones that are more marketplace logistical, and then something briefly on engineering, and then we will move to the panel discussion. So for steel structures and for monopiles and to a lesser degree jackets, but similarly, we have quite a good infrastructure for producing these. And so they can run something through all steps in the operation in a mass production environment. If you want to see how it is done, SIF has a wonderful educational video on all the steps that go through in a production. Concrete is more challenging in this way. And so as Sihan presented onshore, you can need a fairly large region by which you for the production and storage of the segments for onshore. For offshore, there can be even larger challenges because of the size of the structures that you are manufacturing. If you conveniently have dry docks available, and this is a dry dock in Newcastle, then maybe your need for massive cranes is a little bit less because of the way you can do a float out. But otherwise, you have to have an area that you find creative ways in which to be able to cast and move these structures out. As I think many people are looking and working on. While there is no need for a serious vessel or barge to carry out many of these types of float and sink solutions, you still do need them for lowering and placing in a position quite accurately, or you need innovative ways to not do this during the ballast and settling steps. One of the challenges for concrete gravity base is the preparation of the seabed. You have to have this sit rather flat because too much of a tilt puts demands on bearings that you do not want to have. And the one of the other things is that you can have, in particularly off the US East Coast, you have some locations with fairly complex soils such that you have to do dredging and backfilling. And also for scour, you have to extend out the protection for some significant different distance from where the structure is located. While local manufacturing and the jobs it creates is a great advantage for fabrication in the US, the employment rates costs are more expensive than in some other countries, and that creates a challenge that needs to be taken into consideration. Another interesting thing about concrete, and this is a surprise to people who are traditionally from the aerospace mechanical engineering communities who are used to dealing with steel, for which you can know the stiffness quite accurately. For concrete, there's quite a variation in what the actual modulus is, and you have to but it's very important to the dynamic response and thereby the design of the structure. And this is a stress strain plot that shows the relationships for different loading rates. And so your actual stiffness of the structure will depend on the rate of the stressing that is occurring from the different types of actions on the structure. So that creates some challenges as well. You often hear about the carbon footprint concern associated with concrete. There are many different solutions being developed for this, and some ways in which you can do carbon capture, non-pozzolanic cements, and other means by which you can reduce this. But even with that said, the amount of cement that goes into these typical structures is actually relatively modest. For most wind energy, in the term commonly used to looking at CO2 benefits of using wind or solar, people look at what is the payback period in terms of the how much of, if you were producing that energy from fossil fuels, does it cost you actually to create the solar farm or the wind farm? For most wind farms, it's about 6 months. So that is, and so if you operate your wind farm for 30 years, you can proportionally think of the carbon savings that way. Obviously, lots of opportunities and need for innovation for concrete to be a successful competitor in providing support structure solutions for both onshore and offshore. But as has been presented by the other speakers, a lot of very good progress has occurred for this. One of the interesting areas is a project that we've just started for the Bureau of Ocean Energy Management, which is the regulator for offshore wind. The project is centered on trying to address issues associated with corrosion inside of these structures, because once you start putting in cathodic protection and coatings, et cetera, you can develop very bad air and water chemistries. And so we are doing research in that, and we are looking at many things, including the effects of perforations on loadings, as well as what happens for corrosion inside. And we decided it wasn't part of the request for proposals, but we said we also want in this study to look at how these structures can actually be used to improve their marine ecosystem, so that really they serve as artificial reefs, which is very important for what we do to be improving the environment and improving opportunities for the fisheries community. There was a video that came out this week of the wind farm just off the coast of Virginia. And there's a wonderful 7-minute video that they made. Now, this structure's probably only been there for about 2 years, but an incredible ecosystem has developed in these two structures. And the growth that has developed in a very short period of time is enormous. These structures have perforations for pressure release, and there is thought that the flow of water in and out has actually contributed substantially to how quickly the habitats have developed. So the most wonderful thing, I think, for offshore wind is that the structures that are going out there, if they start to become artificial reefs that do good things for the marine ecosystem, as well as are supportive of the fisheries communities, people are going to be much more accepting of a much larger amount of offshore wind energy, which we need for addressing other climate issues. So that was a lot about I would say, marketplace and logistical aspects. Marcus has already talked through some of the differences in the design of onshore and offshore wind turbine support structures, just in terms of the types of environmental loads and other factors. There are many new codes and recommended practice documents for the average structural engineer to become more familiar with in order to work in this industry. There's a large number of unfamiliar load cases. There is this review by a certified verification agent. And then there's also review and approval by a US regulator. We did produce a document, or I should say a document was, I guess I contributed to it as well, in the Innovation Task Group in ACI, published a few years ago, providing some general guidance to people who are new and want to this industry and want to have a basic sense of what the considerations. This was done for onshore structures. There's other documents out there that are very informative for offshore. For determination, another aspect is the determination of the design force values. And Marcus went through some of this, but you have to do dynamic time series analyses, look at many different load cases, as aerodynamics and hydrodynamics, as wave loads, and sometimes you have to use sophisticated computational fluid dynamics software like OpenFOAM. High cycle fatigue, fatigue critical design can be the case, particularly as we go for large monopiles supporting big turbines in deeper waters. Soil foundation structure interaction can be non-trivial. With floating structures, different types of challenges have to come in. And this is, a lot of this is unfamiliar and new territory for most structural engineers, which creates a bit of a challenge. Usually, the structural engineer is working within a design team, and the structural engineering is relying on the original equipment manufacturer, like an MHI Vestas or a General Electric or a Siemens Gamesa, et cetera, to actually do the complex analyses. And so the structural engineer is often providing the dimensions and characteristics of the structure. The OEM does the analyses, and then that comes back to the designer, structural engineering designer, and you iterate through the process. How much optimization occurs very much depends on the specific project and the amount of time available to finalize some of the design selections. There is a sort of what I think many people think is a very major problem presently, is that for the structural details and the performance of the structures in the field, that is held as proprietary information for reasons of competitiveness. But what it does mean is we have a fair much of a lack of public information to actually advance our codes of practice and our best practices. And this will be a continuing challenge moving forward. Another challenge for the U.S. is, despite the names of some of the wind farms, by and large, it's large oil and gas companies in Europe which have acquired the areas. U.S. offshore oil and gas industry, which is very large, have not yet really heavily invested in renewables. There was an announcement earlier this week that Iberdrola is investing $8.2 billion in a UK wind farm. I know that British Petroleum has invested over $1 billion in a US wind farm, but we're not presently seeing that from the US oil and gas companies, and hopefully we will in the near future. This is my last slide before we go to the panel session, and I just remind us of sort of where we are. We're at the very early stages in terms of the amount of onshore and particularly offshore wind energy development that I think we expect to happen in the coming years. And this is a worldwide plot of how the electricity demand is going to increase. And in countries in which are still developing, you can imagine why that would be the case. But even for countries like the United States, which is present electricity generation consumption is 4 terawatt hours per year, it is expected to grow as we shift to electrification of our vehicle fleets and in many industries, because renewables are good for electricity generation, of course. In thinking about the magnitude of this challenge, you do recognize it's going to require significant investments. Things I say are looking relatively bright in terms of what bills will actually get through US Congress and the dollars that are going to be made available for the energy transition. As I think a lot of people have been thinking about where should those investments be to drive this industry, and I always as a little bit of a jovial element, I found myself humming a song by a particular musical group, and in their song is, "If I had $1 million, I'd," and actually it should, as we think about this industry, maybe it's a little bit more, if I had $1 billion, or if I had $10 billion, what would you do? Well, the U.S. I think is talking about, and I think it's important that there's these heavy investments in infrastructure. For port facilities, fabrication yards, strong quaysides, installation vessels. We need to develop the workforce, and that includes leaders in the industry. So there's a big educational aspect as well as long-term thinking. Another one that comes to mind is, and it's sort of this challenge of the time it takes to produce concrete support structures right now. And how do we perhaps move to an environment in which we can manufacture structures without necessarily this closed relationship with an original equipment manufacturer? And there are reference wind turbines and other information that's becoming more available, I think, with time, such that perhaps we can start thinking about how we manufacture a general concrete, for example, gravity base or floating structure for a particular turbine class, as opposed to it just being for a particular manufacturer's turbine. And so I wish to thank my speakers for their presentations.